Chapter 13, Section 5, Objective. Learn to identify and graph exponential functions. Essential question, what does an exponential function look like? An exponential function has the form f of x equals a times r to the x, where a is not equal to 0, r is greater than 0, and r does not equal 1. Similar to what we did with geometric sequences, you have your a, which is kind of like your initial term, your r, which is your common ratio, and then your x, which is the number of times you are going to produce your exponential function. A function rule that describes the pattern is f of x equals 15 times 4 to the x, where 15 is a sub 1, the starting number, and 4 is the common ratio. This type of function is an exponential function. In an exponential function, the y-intercept is f of 0 equals a. So the y-intercept is your starting value. Let's create a table for the exponential function and use it to graph the function. So we'll use the values -2 through 2 for x. And remember, order of operations means we're always going to do the exponent first. So we would start by taking 2 to the -2nd power. And just a quick refresher, when you have something to a negative power, that means it becomes a fraction. So it becomes 1 over 2 to the 2nd power, which is 1/4. 2 to the -1st would be like 1 over 2 to the 1st, or 1/2. So when you have those negative exponents, it's important to remember to put them into a fraction form, or decimal, but fraction might look a little bit better. Then we multiply by 3 because that's part of our exponential function. So we get 3/4 for the first one. We get 3/2 for the second one. Anything to the 0 power is 1, so 3 times 1 is 3. And 2 to the 1st power is 2, 3 times 2 is 6, and 3 times 4 is 12. Graphing these is a little bit trickier simply because your numbers are sometimes going to shrink and get very, very small, or quickly enlarge and get very big. So you may not be able to fit everything all the time, or you may have to do your best. So for example, 3/4 and 3/2, we do our best to get those in the right locations. But what happens is you're going to see a curve. We call it the exponential curve. Whenever you have something to an exponent power with an x that could be any different values, you're going to see this curve either increasing or decreasing. Let's try f of x equals 2/3 to the x. So 2/3 to the -2nd power becomes a reciprocal, and then we take the square of that, 2.25, 1.5, 1, 0.67, 0.44. Again, tricky to graph because we don't know the exact locations, but we get the best we can. You can see here we made our graph a little bit smaller, and we could spread out the 1 through 5 a little bit more. And this one is decreasing, or decay is what we call this. Linda invested $200 in an account that will double her balance every 3 years. Write an exponential function to calculate her account balance. What will her balance be in 12 years? So as an equation, 200 is her starting amount, or A. 2 would be what we would put for the common ratio because it's doubling every 3 years. And x is the number of 3-year periods. So x is not 12, because 12 is the total number of years. X would be 4 because you will have 4 3-year periods in that time frame. So take 2 to the 4th times 200, and you get $3,200. In the function f of x equals a times r to the x, if r, the ratio, is greater than 1, and a, the starting value, is greater than 0, the output gets larger as the input gets larger. In this case, f is called exponential growth. A bacterial culture contains 5,000 bacteria, and the number of bacteria doubles each day. How many bacteria will be in the culture after a week? So on 0, 1, 2, 3, those are the number of the days of the week. So 0, we call that the first day, but we put 0 because nothing has doubled yet. So on day 1, it doubles. On day 2, it doubles again. And day 3, it doubles again. So we're not just doubling the starting amount, we're doubling the amount from the previous day. So our function for that would be our starting value of 5,000 times our common ratio, which is 2 because we're doubling, to the x power. So if a week is 7 days, we're going to let x equal 7 because we're looking at 7 days for the week. So we take 2 to the 7th times 5,000. We get 640,000 at the end of 7 days. In the exponential function, f of x equals a times r to the x, if r is between 0 and 1, so we're talking about a fraction or decimal, and a is greater than 0, the output gets smaller as x gets larger. So it all comes down to our ratio. If our ratio is a fraction less than 1, then we're going to have exponential decay. If our ratio is greater than 1, we'll have exponential growth. So borium-267 has a half-life of 15 seconds. Find the amount that remains from a 16 milligram sample of this substance after 2 minutes. So we have the number of seconds listed, the number of half-lives, and then the borium amount. So after this 0 number of half-lives, we would have 16 to start. That would cut down to 8 milligrams after 1 half-life, 4 milligrams after 2, 2 milligrams after 3. So let's write our function. Our starting amount is 16. Our common ratio is half, just like a geometric sequence. So 16 times half to the x power. 2 minutes is 120 seconds. Divide 120 seconds by 15 seconds. There would be 8 half-lives. The reason we need to do that is because half-lives are every 15 seconds. So we need to figure out how many times it's going to be cut in half in 2 minutes. But we need minutes to be in seconds to do that. So we substitute 8 for x. We take half to the 8th power times 16. There will be 0.0625 milligrams of borium-267 left after 2 minutes. So growth and decay exponentially can be very dramatic, and it can move very quickly either direction. Make sure you have that formula and see if you can figure out the comparison between the geometric sequences that we worked on and the exponential growth and decay.